computer. Okay. All right. So we can start now. Today we're going to talk about the eigenvalue problem related to matrices, transformations, and vectors. This is a very important topic in linear algebra. You'll find applications of these eigenvalue problems in different areas in physics, in particular the classical mechanics and quantum mechanics. All right. So when a square matrix acts on a vector x vector, then the resultant vector is in general very different from the original vector, because you apply the matrix on the column vector x and you try to change it, right? For example, rotation, you try to rotate the vector, so the resultant vector will be very different. However, there may exist certain non-zero vectors for which the resultant vector is actually proportional to the original vector. In other words, it is equal to the original vector multiplied by a constant lambda. All right. In other words, as shown in equation 1, when we apply the matrix A on the column vector x vector, we'll get back the x vector with an additional prefactor lambda. Such a vector is called an eigenvector of the matrix A. And the constant lambda is called an eigenvalue. All right. So this is equation 1 is called the eigenvalue equation of the matrix A. All right. Now, let us look at an explicit example. Say if A is a square matrix given in equation 2, so this is the square matrix A, then the eigenvalue equation can be written as this, shown in equation 3. So the matrix A acts on a certain column vector, will give you back the column vector multiplied by a prefactor lambda. All right. Then we perform the matrix multiplication explicitly. Then we obtain a system of two linear algebraic equations. Actually, these two equations are homogeneous linear algebraic equations. Okay. Now, obviously the solution is trivial. X equal to 1, x2 equal to 0. In other words, if we have a null vector, then the null vector is a trivial solution of this equation, of this set of equations. However, if we are interested in non-trivial solution, then we have to satisfy certain condition, i.e., that is, the determinant of the coefficient matrix of this set of two linear algebraic equations must vanish. All right, so the coefficient, the first one element of the coefficient matrix, 1, 2 element of the coefficient matrix, 1, 2, 1 element of the coefficient matrix, and 2, 2 element of the coefficient matrix. So the determinant of this coefficient matrix must vanish. Since this is a 2 by 2 determinant, though, so we will obtain our quadratic equation, and we can obtain the roots immediately. Okay, so the two roots of these equations are lambda equal to 1 and lambda equal to 7. All right, for lambda equal to 1, we substitute back into equation 4. Okay, now we will immediately see that these two equations are redundant. In other words, they are not independent of each other. So we only have one independent equation. All right, so we substitute lambda equal to 1 into the first equation. Then we have a we know that x1 must be proportional to x2 according to this ratio. Okay, if x1 equal to 2, then x2 must be equal to -1. All right, so this is the solution, non-trivial solution corresponding to the eigenvalue lambda equal to 1. Or on the other hand, if we pick the eigenvalue lambda equal to 7 and substitute it into the same equation, the first equation in equation 4, then we will obtain another non-trivial solution, i.e. x1 equal to x2 equal to 1. All right, so the eigenvector corresponding to the eigenvalue lambda equal to 7 is this column vector 1, 1. The eigenvector corresponding to the eigenvalue lambda equal to 1 is this column vector 2, -1. Okay. Now, keep this in mind. These two eigenvectors are not normalized yet. In other words, the norm of these two eigenvectors are not equal to 1. What we are really interested in are the normalized eigenvectors, normalized eigensolution. Okay, in other words, we need to find a unit vector in the same direction as these two eigenvectors. All right, such that the norm of the two eigensolutions equal to 1. Now, in general, the eigenvalues of a square matrix are determined by the second equation. In equation 8, where I is the identity matrix. If A is an n by n matrix, there will be n roots. In other words, we need to solve. We need to find the roots of an equation of degree n. Okay. Not necessarily all different. The n roots are not necessarily all different. Some of them may be repeated. In addition, provided that A is a symmetric matrix, it can also be shown that eigenvectors corresponding to different eigenvalues are orthogonal. All right? For symmetric matrix A, the eigenvectors corresponding to different eigenvalues are orthogonal. All right? That is, the inner product or scalar product between any two eigenvectors with distinct eigenvalues must vanish. Now, this property you will encounter this property in Professor Ching's course and also in quantum physics course. All right. Okay, so keep this in mind. These are the basic properties of the eigenvalue problem associated with a square matrix A, in particular a symmetric matrix A, right? Now, if we have a matrix, let's see. Okay. Now, if we are given a matrix A and we want to diagonalize this matrix, then what should we do? All right, we will see the applications of the diagonalization of symmetric matrix later. Okay, in a given example that I will discuss later. Now, if we are given a symmetric matrix A, I want to make it diagonal. Then, in other words, we want to transform this matrix into a one diagonal matrix with the diagonal elements being non-vanishing. All the other elements are 0. Okay. All right. So first of all, what we need to do is to solve the eigenvalue equation associated with this symmetric n by n matrix. All right. So we are going to find all the eigenvalues. In this case, we will have n eigenvalues and also n eigenvectors, the n non-trivial solutions. Okay, and we try to normalize these n eigenvectors in such a way that the norm of these normalized eigenvectors are equal to 1. Okay, all the norms are equal to 1. So how do we do that? Let us construct a square matrix Q, we call it Q, as follows in terms of these normalized eigenvectors. So this is the first column contains the first eigenvector, the second column the second eigenvector, up till the nth column with the nth eigenvector. All right. So in the first column, the first element is the first element of the first eigenvector, second element, the second element of the first eigenvector, and keep to and the last element will be the last element of the first eigenvector. All right, and then we multiply the original n by n matrix A to this Q vector, a Q matrix, this Q matrix. All right, square matrix, and we get this. Looks very complicated, but actually you can easily recognize that this matrix can be decomposed into this one. All right. Then the next step, we multiply this product resultant matrix by the inverse of the Q matrix. All right. By the inverse of the Q matrix. Then you can see right away, if I multiply both sides by the Q inverse, the right-hand side will give you a diagonal matrix, all right, because the Q will be removed away. Okay, so let's look at a given explicit example. A equal to A11, A12, A21, A22, and Q. The first column is the eigenvectors of the matrix A. The second column is the second eigenvector of the matrix A. Then we multiply A to Q. Okay, so A11 times U11, A12 times U12, add them together. A11 times the first element of the second column vector, A12 times the second element of the second eigenvector, so on and so forth. Then we get this, a complicated a square matrix, a resultant square matrix. Now, since the application of the matrix A on each eigenvector will give you this, as shown in equation 13. So A11 times the first element of first element of ith eigenvector plus the A12 times the second element of the ith eigenvector. All right. So what is this? What is this? We claim that it will give you back the original eigenvector with this additional parameter, prefactor, lambda I. All right. So this is equal to lambda I times the first element of Ui. This is equal to lambda I times the second element of the ith eigenvector. All right. Then realizing this, then we compare with equation 12. What will we get? So we can easily get that this whole thing is equal to this. Am I right? Because replacing this by lambda I ui1. Okay. This replaced by lambda 2 u21. Okay. This is, what is that? That is a lambda 1 u12. Okay. u12. This is lambda 2, according to here, is lambda 2 u22. All right. So we can split this into two two matrices as shown here. So actually, that is equal to QB. All right, QB. Now B contains all the contains only the diagonal elements, and the diagonal elements are simply the eigenvalues of the matrix A. Right. So B is equal to Q inverse times Q is a diagonal matrix. Okay, get it? So that's how we diagonalize a matrix A. And the additional thing is eigenvalue or something else. Mohammed, can you explain a little bit about your question?
Can you hear me?
Yes.
Okay, so I just want to ask that UI is its normalized eigenvector.
Right.
Represents. So is there other thing related to eigenvalue or something? It's totally unrelated to that.
Now, for each eigenvalue, we have a corresponding eigenvector. You normalize eigenvector.
Yeah.
Is that what you want to ask?
Yeah. I just wanted to ask that UI is a normalized eigenvector, right?
Right.
So
right,
that
right.
lambda I is a normalized eigenvalue, or
eigenvalues just eigenvalues, not normalized or not.
Okay, eigenvalue. Okay.
All right. Eigenvalues are simply the prefactor, additional prefactor. Okay. Now, so that's how we diagonalize a given matrix. Good point. How do we know the Q inverse exists? Okay. Now, first of all, what is the requirement or the constraint, precondition of the existence of the inverse of a matrix? The determinant must not be equal to 0, right? So, okay, non-singular. That's good. That's good. Now, number 3. Be patient. Be patient. So let us double check. Now, Q is an orthogonal matrix. Okay, let's check. We take the transpose of the Q, all right, and multiply it to Q. So we just take the transpose, interchanging columns and rows of the matrix Q, and that is the transpose, all right, and then multiply to Q. Okay, now that means what is the transpose? That is, we have U11 here and a U21, am I right? And here we have a U11, U12, and then we have the Q here. We multiply together. In other words, we're taking products, inner products of different eigenvectors. We take the first row of the Q transpose, dot into the first column vector of the Q matrix. Of course, that is equal to what? 1. If we take the first row vector, that is the first eigenvector, dot into the second column vector of Q. The second column vector of Q is the second eigenvector, right? First eigenvector dot into the second eigenvector, of course we get 0. So automatically we have a diagonal matrix, which is actually the identity matrix. Okay, so we have shown that in fact the Q transpose is equal to the Q inverse. All right, and we have a special name for this kind of matrix, orthogonal matrix. All right, so the Q inverse in this case is simply the Q transpose. All right, so it can be done very easily. Furthermore, it is obvious that by a suitable orthogonal transformation, the eigenvalue problem, okay, the original eigenvalue problem, if we perform this suitable orthogonal transformation, has a very different form. Let's take a look at it closely. So we apply the Q transpose to both sides, and then insert an identity matrix in between A matrix and the column vector X vector, okay? This identity matrix can be written as the product of Q and Q transpose, because Q transpose is the inverse of Q, okay? Now, what is a Q transpose A and Q, or Q inverse AQ? That is the B, all right? And Q transpose X on the X vector is Y vector, okay? Now, you can see that after the suitable orthogonal transformation, we have another eigenvalue equation involving B matrix and Y column vector, right? However, both the original eigenvalue equation and the transformed eigenvalue equation have the same set of eigenvalues. In other words, the orthogonal transformation will not change the eigenvalues of the original eigenvalue equation, or will not change the eigenvalues of A. All right? So this is a very important properties of orthogonal transformation. In other words, when you rotate, when you perform rotations, and you have the moment of inertia, inertia matrix or tensor, and you realize that the eigenvalues will not change by the orthogonal, by the rotation. All right. And when you go to quantum physics, it will be more interesting. You try to solve the eigen or the time-independent Schrodinger equation, i.e. the eigenvalue equation of the Hamiltonian operator, all right, or the energy operator. And you will realize that after the transformation, it has a special name, unitary transformation, all right, because in general it is complex. The eigenvalues will not be changed. So through, as shown here, we can always try to simplify an eigenvalue problem by proposing a suitable orthogonal transformation, okay? Once we find that suitable orthogonal transformation, solving the resultant eigenvalue equation becomes trivial, because the resultant transformed matrix B is diagonal, all right? So we have a lambda 1, y1, lambda 2, y2, up to lambda n, yn, okay? So this is a very nice way to solve eigenvalue problems. However, how to find this suitable orthogonal transformation is another story. All right. Sometimes when you are experienced with playing with the orthogonal transformations, you can identify the suitable orthogonal transformations by inspection. Just like when you do integrations, some guys are very skillful, the other guys are very clumsy. Keep applying the method of integration by parts. However, the other guys are very smart due to a lot of practices. They can find a suitable substitution right away, and the integral becomes trivial. Just like here, when you practice a lot, sometimes when you encounter a new problem, and you can spot a suitable orthogonal transformation right away by inspection, okay, rather than going through all these procedures, solving a set of linear homogeneous linear algebraic equations. All right. Okay. Any questions so far? Any questions? Now, if you don't have questions, then I have questions for you. First of all, now if we have a 2x2 matrix, of course it's trivial. Then we can solve the eigenvalue problems right away. Okay, just like here, because a 2x2 determinants will give you a quadratic equation. Then we get the eigenvalues right away by applying the standard formula. Okay, now if we have a 3x3, what will happen? What should we do? Cubic equation, yes. Then, what do you know about the cubic equation? Of course, it is difficult to do. Yes, it is difficult to factorize. Yeah, sometimes you can factorize it, but usually very difficult, right? Just like in equation 5 here. Now, you can factorize it very easily because 7 here, so 1 times 7 is the only possible case. And since we have -8 here, so it must be -1 times -7, right? So you get the answers right away. However, for cubic equations, there are usually 3 roots. And some of them may be complex, right? Yeah, good idea. Use calculator. If you have the programmable calculator, yes. Graphical method, yes. That is a good approach too. Now, Wolfram alpha, yes. Good idea. Now, go. Now, this is my advice. Get a copy of Mathematica, okay? Get a copy of Mathematica. Then if you have a cubic equation, type it in. Then you will get all 3 roots. Of course, some of them are not admissible if you require the roots are real, all right? But Mathematica will give you the answers right away for cubic equations, all right? Or you go back to some old textbooks on algebra, then you will find that the cubic equations have closed form solutions. In other words, the solutions can be written in terms of radicals. All right. So cubic equation is okay. Now what happened? If we have 4x4, if we have 4x4, we skip the question. Yeah, that is a good idea, and work on the others during the exam. Don't waste time. Yes. So any suggestions? If we have 4x4, that means we have a quartic equation. Any suggestion? Decompose the matrix. Not all. It cannot be done all the time. So again, go to Mathematica. Okay, go to Mathematica. Mathematica will give you closed form solutions in terms of radicals. Okay, 4x4. Okay, quartic equations can have closed form analytical solutions. or you can go back to some old textbooks on algebra, high school algebra. We sometimes call it Cartan's equation, Cartan's solution, but actually the solution was given by another guy, all right? So quadratic equations can be done. If you don't know about the quadratic equations, then of course numerical methods will do, the Newton's method, but you have to give some guess, all right? Or you plot it out, you plot out the polynomial and see how many roots do you have. Of course, when you plot it out, you only you can see only the real roots. Now, if we have 5 by 5, what will happen? Any idea? Any idea? 5 by 5. Mathematica. No way. Yes, it cannot be solved analytically. Okay, you don't have a closed form, a simple formula, a simple formula to give you the answer. All right. So, but Mathematica still can help you. It will give you numerical solutions or very complicated analytical solution. Okay. So beyond quadratic equation, beyond 4 by 4 determinants, you need to resort to numerical methods to find the roots. There are many methods can be done, Newton's method, secant method, or many others, all right, complicated ones. You can use commercial packages like Mathematica, MATLAB, MathCAD, all these software to help you to do it, all right? So, all right, anyway, so just for fun. So keep this in mind. We can solve algebraic equations up to quadratic equations only. All right. I mean analytically in closed form. All right. Okay. Okay, let us take a 5 minutes break and then we come back to some examples, some applications of Newtonian mechanics, making use of all these mathematical tools. All right, 5 minutes break.
Professor Low?
Yes.
Yeah, about the homework submission, like we had the meeting and we consult some of the students and we decided to use the Blackboard for homework submission.
Yes, right. Can you three handle that?
No, I think like we cannot do it now. Like you need to open the Access and like give three of us the you need to give us the access so that like we can then handle it. Yeah.
Okay.
So you have to be the one to open up the Blackboard.
How can I do so?
Well, we're not sure.
Now, how about this? After the class, are you in the office now?
Yes.
Okay. How about the lecture class? Come to my office, and we can talk about it.
Okay. So like, how long will you stay in the office today? Because I have a course later. Yeah.
When?
12:30.
12:30. Okay.
Yeah.
This lecture class will end 1:15. When will your lecture class finish?
Like 2:15, I think.
2:15. I
Yeah.
see. Okay. Just come after the class.
Okay. Okay.
So we can talk about how to set it up.
Oh, okay.
Because I have no experience in setting up the Blackboard.
Okay. Yeah. Well,
Right.
me neither.
Okay.
Okay.
Thanks a lot.
Yeah.
Thanks a lot.
See you later.
All right. All right. Now, in the following, we will discuss some applications of the Newtonian mechanics using the mathematical tools that we have just discussed. I get a question. Mohammed, we cannot access lecture recording after 1 week. I don't know. I just post it there, post it on the web page, so you can click on it. I'm not sure. I can upload it again if they are not there. Just remind me. Is it okay? If the lecture recordings are gone, then just let me know. Then I try to upload it again. All right. Okay. Now, the first example we are interested in is the two coupled simple harmonic oscillators. As shown in the figure, we have two blocks of mass m, of the same m. Each of them is attached to either wall by a spring. And these two blocks are connected to each other via a spring. All three springs have the same spring constant, all right? And here you can see that x1 represents the displacement from equilibrium position. x2 is the displacement from equilibrium position of the second block, all right? So we draw as usual, we follow the standard steps of solving Newtonian mechanics problems. We write down we draw the force diagram for block number 1 and another force diagram for block number 2, all right? So on the left-hand side, we have mass time, the acceleration of the block number 1. On the right-hand side, we have restoring force applied by the left spring, okay? So we have a minus kx1, the restoring force. At the same time, we assume that the x2, there is a force pulling the block number 1 towards to the right. So we have a k time x2 minus x1, okay? The relative displacement, x2 minus x1. For block 2, the force diagram, in the force diagram, there are two forces. The first one is this. The spring, the first force is exerted by the spring attached to the wall. All right. It tries to prevent the second block coming too close to the wall. So the force is pointing towards the negative x direction. So we have a minus kx2, right? And also by action and reaction principle, there is a force pulling the second block towards to the left. That is equal to minus k times x2 minus x1. x2 minus x1 is the relative displacement of the two blocks. Okay. And then we introduce the natural frequency parameter omega naught, that is equal to k over square root of k over m. All right. So we have two equations. Now this is a set of two coupled second order ordinary differential equations. So we have to solve these two equations. How do we do that? How do we do that? So first of all, we introduce two new variables. We call it x plus and x minus. All right, x plus is x1 plus x2. X minus is x1 minus x2. Sometimes we may use the language that x plus is proportional to the center mass of the problem. X minus is the relative coordinate. All right, so we substitute the x plus and x minus to the set of equations. Okay. Then we have x plus double dot equal to minus omega naught square x plus, and x minus double dot equal to minus 3 times omega naught square x minus. All right. So miraculously, we have decoupled the set of 2 second-order differential equations. All right. And each of these 2 equations have well-known solutions. Why? Because if you take a close look at each of these 2 equations, you realize that they bear a striking resemblance to the equation motion of a simple harmonic oscillator. All right. So we can write down the solution right away because we have learned about this special equation motion from high school. Okay. So the solution for equation 1 is x plus must be equal to the linear combinations of the cosine omega naught t and sine omega naught t. The second equation, in the second equation, the solution must be a linear combination of cosine square root 3 omega naught t and sine square root 3 omega naught t. All right, so we have the general solutions for both ordinary differential equations. Right? How do we fix the a plus and b plus and a minus and b minus, all these four constants? Okay, then we have to impose the initial conditions, initial position displacement for both block 1 and block 2, the initial velocity of both block 1 and block 2. Okay, so here we pick a very simple set. Initial velocities are 0. Initial position for block 1 is x1 naught. Initial position displacement of block 2 is x2 0. Okay, so we substitute these conditions into equation 2 here. All right, t equal to 0. The sine function will give you 0. So we will have a plus and a minus. All right, so we have a plus a minus equal to x naught plus x2 naught. A minus equal to x1 0 minus x2 0. We substitute the second set of initial conditions, i.e. the initial velocities. All right. So we differentiate these 2 equations, these 2 equations again, and set t equal to 0. So the cosine, we differentiate cosine, we get sine, and at t equal to 0, it vanishes. We differentiate sine, we get cosine, something proportional to cosine, and we set t equal to 0, get 1. All right. So we in order to satisfy these 2 initial conditions, we have to force b plus equal to 0, b minus equal to 0. All right. Once we get these constants, our desired solution comes out immediately. x1 is given by this, x2 is given by this. All right. We just reverse the relations here. Now, this is the standard approach. Now, what is the problem? What is the difficulty of solving the set of equations using this method? Especially if we have more blocks. In other words, if we have more subsystems, we will have a set of n coupled second order differential equations, right? Then we have to introduce n new variables in such a way that the n coupled equations are decoupled miraculously. Am I right? Obviously, this is not a simple task. If n is large, say n is 100, then you have to figure out 100 new variables in such a way that all the n all the 100 equations are decoupled. So this is not easy, all right? So this method is good for the case of a few variables, all right? So we need to find an alternative method, which is systematic and doable, all right? Of course, if someone are very smart, very experienced, he can spot the n new variables easily, then of course this is a much better method, right? Because fast. In most cases, we cannot do it. So we have to resort to a systematic approach. Okay, here's a systematic approach. Now we know that the system is a conservative system. It has conservative force. So the total energy should be conserved, right? So we have we write down the total energy, kinetic energy plus potential energy, all right? Kinetic energy is very simple. It's equal to 1/2 m x1 dot square plus 1/2 m x dot square. Now, we can always rewrite this in terms of matrices and vectors, as shown in equation 7 here, right? So it seems that even though we have a system of two particles, actually we can treat it as a system of one particle moving in 2 dimensions. Am I right? So x1 equal to x, x2 equal to y. Okay, they are equivalent. Okay, in that sense. So so we have a 2-dimensional vector here, 2-dimensional vector here, and we have a 2x2 mass matrix. I call it mass matrix. Okay. All right. So we rewrite the kinetic energy in terms of matrices and vectors in this way. How about the potential energy? Potential energy is equal to 1/2 kx1 square plus 1/2 kx2 square. These are the kinetic potential energies due to the 2 springs attached to both walls. How about this potential energy? This comes from the spring connecting the 2 blocks. That's why the displacement depends on the relative displacement. All right. So we have a potential energy given in this form. We try to expand the expressions and collect the like terms. Then we realize that we have this. This whole thing can be simplified to this simple form. All right. Again, we can rewrite this in terms of the matrices and vectors. Okay. Now, but this time is we have something different. We have a cross term here, unlike the kinetic energy term. All right. So the cross term will contribute to the off-diagonal element, off-diagonal elements. Since x1, x2 is the same as x2 times x1. So we separate this term into 2 parts. One is 1/2 k x1 x2. The other one is 1/2 k x2 x1. All right. That's why we rewrite it in this form. Okay. Now, we call this as a column vector, but displacement column vector. This is a row displacement column row displacement vector, and we may sometimes call this as the spring constant matrix. Okay, this is the mass matrix. Okay, now we try to look for an orthogonal coordinate transformation such that the new vector is equal to transforming the original vector by the transformation matrix Q, so that the kinetic energy can be cast in canonical form. That means diagonal form, okay? Now, as you can see, since the kinetic energy term is already diagonal, so any transformations will not affect it, right? Any transformation which can diagonal the potential energy will not affect the diagonal form of the kinetic energy. Okay. Now, so we want to diagonalize the matrix K. To do that, we have to solve the eigenvalue problem of this matrix K. To do that, to find the non-trivial solutions, we have to force this coefficient matrix, the determinant of this coefficient matrix associated with the matrix K to vanish. All right. Now you expand this, you will get a quadratic equation in lambda. And you can easily see that lambda admits two possible solutions. One is K over 2, the other one is 3K over 2. All right. So for K over 2, lambda K over 2, we substitute it back into the two set of equations. All right. So K minus K over 2 times x1 minus 1/2 K x2 equal to 0. All right. So this is the normalized eigenvector corresponding to the eigenvalue lambda equal to K over 2. We do the same thing. And we have another eigenvector, normalized eigenvector corresponding to the eigenvalue lambda equal to 3K over 2. All right. Once you obtain the two normalized eigenvectors, we can construct the orthogonal matrix Q. The first column of Q contains the first normalized eigenvector. The second column contains the normalized second normalized eigenvectors of K. All right. Then make use of this orthogonal matrix at Q. We can transform the K, right? Okay. So we can replace this by the eigen, after transformation, this will go to a diagonal matrix. And x1 will go to x1 prime, x2 will go to x2 prime, right? That's given like this, okay? So the off-diagonal terms will disappear. So we have the kinetic energy given here, potential energy given here, all right? Now you can see that the total energy of this system, of the transformed system, can be decoupled into two non-interacting blocks, am I correct? X1 is not connected to X2 prime, X1 prime that is not connected to X2 prime. So we have two contributions to the total energy. One comes from this kinetic energy plus this contribution of the potential energy for block number 1, transformed block number 1. Second contribution of the total energy comes from the kinetic energy of transformed block number 2 and potential energy of the transformed block number 2, all right? So if you look at the transformed block number 1, we have a kinetic energy like this and a potential energy like this. We know right away it is a simple harmonic oscillator. Am I right? So the x1 prime must be a linear combination of cosine omega naught t and sine omega naught t, right? The block number 2 will have kinetic energy and potential energy, and we can immediately see that it represents a simple harmonic oscillator of natural frequency square root 3 omega naught. So the solution must be given as a linear combination of cosine square root 3 omega naught t and sine square root omega naught t. So we don't have to solve any differential equations because we know the solutions by our heart. Okay? So once we know the x1 prime and x2 prime, we transform back, okay? We apply the inverse of Q to this x prime vector to get back the original vector, x vector, okay? So x1, x2 are given by this, okay? Then we impose the initial conditions, initial displacement, non-vanishing, initial velocities, vanishing, okay? So D1, D2 must be 0, 0, and C1, C2 are given in equation 17. As a consequence, as a result, we obtain the same results as in equation 15, equation 5, and equation 6, just like before, okay? So it is obvious that this alternative approach is particularly useful when the number of coupled oscillators is large, because we do not need to solve a system of coupled second-order ordinary differential equations. So this approach is systematic, easy to handle, all right? So this is a preferred approach for solving a system of coupled oscillators, all right? Of course, if you're smart, experienced, you can tell me right away that by inspection, this is the solution. You are welcome to do so, even in the exam, all right? Even in the exam. Okay, any questions up till now? So this example illustrates the application of orthogonal transformation, or the diagonalization of a matrix. Okay. Any questions? Now, to be honest, this example is deceiving. It's deceiving you. Why? Because this is a two-dimensional problem. If you have n coupled oscillators, then you have a polynomial of degree n. You want to find the roots of a polynomial of degree n. Then you have to search the roots, find the roots numerically, right? One by one. And then for each numerically found eigenvalue, we have to put it back into the equation and get the corresponding normalized eigenvectors, right? So it is not as simple as you think, but it is systematic. What you need to do is to follow the rules. Say, write a computer program to take care of all these calculations. Or you can call a computer, commercialized packages like Mathematica, MATLAB, Mathcad, Maxima to do the calculations for you, right? Systematic is the key thing. Nothing else. All right? Any more questions? Any questions? Any questions? I have a question for you. Are there physical meaning to those transformations? Yes. You are performing rotation, right? If you have in this case, we have a two-particle system, but we can treat it as a two-dimensional problem of a single particle, am I right? So you try to rotate the axis in such a way that there are no cross terms. That means the x components execute motion independently. The y component execute its motion independently. All right. So you are trying to get the principal axis. If you have n particles, then you can think of it as a n-dimensional problem of a single particle. Okay. Now, then I have a question for you. Here we have a total energy expression. It contains kinetic energy and potential energy. If you take a closer look at the kinetic energy and also the potential energy, what do you see? Can you see that the total energy is in fact in quadratic form, right? The total energy is in quadratic form. So we try to diagonalize this quadratic form in such a way that instead of summing n by n terms, we sum n terms, right? Okay. Another example, one-dimensional driven damped oscillator. So I think all of you have seen this example before. This is the acceleration, this is the damping part, and this is the spring, natural spring force. This is the driven force. Now, it is well known that the solution consists of two parts, namely the general solution of the corresponding homogeneous equation. That means without any force, okay? Setting this external force equal to 0, and we find the general solution for this second order differential equation. In a particular solution, one of the solution of this equation, all right? Then combining them, then we have the general solution. What is the homogeneous solution corresponding to this problem? It must be in exponential form, right? This general solution consists of two independent solutions. Each of them has the exponential function form, all right? Why? You can see that you differentiate the solution once, you get back something proportional to the solution itself. You differentiate twice, you get back something proportional to the function itself. So it must be exponential functions. Okay, so then you guess the solution to be in this form and then substitute it into this equation and find the corresponding parameters for the lambda plus and lambda minus. Okay. How do we, the toughest part is how do we get a particular solution to equation 1? All right. It depends on the given t, ft, depends on the given ft. Say, for example, if we have a constant force, then it is trivial. If xt is a constant, then these two terms will vanish. And this constant cannot be arbitrary. It must be equal to this, okay? Otherwise, it won't work. It is not one of the particulars, one of the solution of this equation. So when we have a constant force, a particular solution, a desirable particular solution is given by this, okay? It is a constant. If ft is linear in t, by inspection, the desired particular solution takes this form, a linear function of t. Okay, this is my advice, but how can I know if this is linear in t? So if this is a linear in t, it depends on t only, does not have a constant term. Then after differentiating this particular solution, we get a constant, right? So this constant cannot be cancelled out by this ft. So we have to require that xt has a constant term as well in order to cancel that. So we take this as the trial solution for the particular solution and substitute it into equation 1, that's what we get. All right. Then we collect the like terms and set each of these like terms in equal to 0. Okay. So for the constant term, gamma A1 plus omega naught square A naught equal to 0, and omega naught square A1 equal to F1 over M. We have 2 unknowns and 2 equations, so we can find the 2 unknowns right away. All right. So for constant force, trivial. For force linear in T is also simple. How about quadratic? Then by the same token, we have to require the particular solution to be a quadratic function, a general quadratic function of t. Okay, and then we substitute it into equation 1 to the damped simple harmonic oscillator equation. Okay, then we have 2a2 for the second derivative term. First derivative term will give you this. The natural frequency term will give you this, and this is driving term. We collect the like terms. Constant term, linear in T, quadratic in T. All right. So we have 3 unknowns, 3 equations. Again, we can solve it. All right. So these are the solutions. Here is an exercise. What will you do if you have a time varying force of this particular form, a polynomial in T? A polynomial in T. Polynomial of power T plus 1. Now remember that if it is a constant force, we use a constant. If the force is linear in T, we use a solution, a general linear function in T. If we have a force function quadratic in T, then we have a general, the particular solution of general polynomial of degree 2, right? So in this case, I think you should use a polynomial of degree n. Am I correct? And then how should we, what's next after assuming that? Using a polynomial of degree n, all right? As a trial solution, what will we do next? Any idea? Any idea? Substitute it and work out the math. Hooray, you get it. Is there a better way? Is there a better way? Is there a better way? Gaussian elimination, superposition. Okay, tell us how. Can any one of you tell us explicitly how you will do it? Trần Văn Mòn, can you tell us how you can do it? Trần Nhân Mong. Yes. So we go to the problem ft equal to fn t to the power n. Am I correct? N equal to 1, equal to 0, equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to whatever you want. All right. And then combine them together is the solution. Okay, let me say it again. Now, if you have this general form, in principle, we should try a polynomial of degree n for the particular solution, right? Because if you follow these three examples, you know that you should a polynomial of degree n is the way to go. Okay. However, if you really do so, you'll get a mess, very complicated. All right. So this is not the best way to do it, but this is the way to do it. Okay, one way to do it. Now, the best way to do it is as follows, as suggested by Trần Nhân Mong. You are hardworking students. So I have done the calculation for constant force, for linear force, linear in T, and also quadratic in T. So you can keep doing, right? In fact, it will be very simple. So keep doing it up to, say, T to the power 10, for example, T to the power 10. All right. I think in practice, it is good enough. Then these solutions can be stored, or you can store all these nooks with you. Okay, either in a computer file, or you write it down, right? So you store all these solutions. So for t squared, you have this solution given in equation 8 and equation 11. All right. For t linear in t, for ft linear in t, you have this solution. For a naught equal to and a1 given by 7. All right, and so on and so forth. For t3, you do it again. T4, do it again. T5, do it again, up to T10. All right. So you have 10 solutions with you all the time, right? So if someone asks you to give a particular solution for a time varying force of the form like this, up to capital N equal to 3. So you just add the first three solutions together. All right. Up to 5, you just copy the 5 solutions and add them together. Okay. With the appropriate prefactors F2, F1, F2, F3, F4, and F5. If N equal to 10, then you just add the 10 solutions together. Okay, because you always have your 10 solutions with you all the time. It will not change. Once you solve it, once you solve these 10 solutions, they are always there. They always work. Okay, that is the idea. All right. Of course, if someone asks you like this, right, ft is a sinusoidal function. You're in trouble. Say, for example, this is a cosine function, then you're in trouble, right? But they are interested in small t. short time solution. That means the time will not go too long. It's only for, say, a certain period. Okay? Then actually you can represent your cosine function by a power series and keep up to a certain term, right? So again, it is a polynomial. And then you can make use of this trick to get your answers. Okay? Now, however, if you are really interested in getting the exact particular solution for this kind of sinusoidal driving force, what can we do? The trial solution must be a linear combination of the cosine and sine functions, cosine omega t and sine omega t. Why? Take a look. If ft is a cosine omega t, then xt, in order to cancel the driving force, must be a function of cosine omega t, right? However, differentiating this cosine omega t will give you sine omega t. And differentiate once again, you get cosine omega t, right? So on the left-hand side, you have linear combinations of cosine omega t and sine omega t. So your solution must involve both of them, okay? Even though the ft contains cosine omega t only. Or ft contains sine omega t only, we still have to try a linear combination of cosine and sine omega t as the trial solution, okay? So in general, if we have a sinusoidal ft given as a linear combination of two cosine omega t and sine omega t, then the desired particular solution must take this form, right? Then we substitute this trial solution into the equation and collect the like terms and set the coefficients, the corresponding coefficients equal to 0. Then we will get these two equations. We have two unknowns and two equations, so we can get these two unknowns right away, all right? Okay, here are two exercises for you. If you are asked if the ft are periodic functions, that means if the ft can be expressed as a Fourier series, then what is the particular solution? The particular solution must be a Fourier series as well, right? However, once you know this solution, the solution for this case, working out the solutions for Fourier series can be done by means of the principle of linear superposition. Okay, just like the polynomials case. So it's not difficult. Another exercise, if we have a non-periodic time-varying force and which has this particular property, it is integrable, then what can we do? If you have studied the Fourier transform, then obviously you apply the Fourier transform for your particular solution. All right. Just curious, have you studied Fourier transform before? No, that's fine. Forget it for the time being. I think Professor Ching will teach you about Fourier transform. It's not a requirement for this course. Somehow I just want to tell you that even for non-periodic time-varying force can be done if it has these particular properties. Okay, it can be done by Fourier transform. Okay, so far so good. Any questions so far? I think most of you have studied this damped driven harmonic oscillator before. So this is only a review. Okay, the last example, double pendulum. All right, so first of all, we identify the coordinates of the masses. The mass is number 1. So the x coordinate, L sine phi. Y coordinate, L cosine phi. How about the second particle? The x coordinate, L sine phi plus L sine psi. Y2 is equal to L cosine phi plus L cosine psi. All right. We want to find the velocities. So we differentiate x1, differentiate y1, differentiate x2, differentiate y2. All right. So we get these velocities. Then we can write down the total energy, kinetic energy, potential energy. Okay, so the kinetic energy, when you try to simplify the expressions, and you'll find that there are two variables are independent, the phi and psi. All right, so the kinetic energy depends on phi dot square, psi dot square, and also phi dot, and there's a cross term depending on phi dot and psi dot, and also the difference of the angular displacement. All right. Potential energy, again, is straightforward. Minus mgy1 for the particle 1, minus mgy2 for the particle 2, and then we substitute in the expressions for y1 and y2 and simplify. We find this. All right. Okay. What's next? Then we have the total energy. And we find that they are very complicated. And according to the Newton's second law, we can figure out, we can apply the Newton's second law to get the equation of motion, but doesn't make much meaning here. So we want to study the system in some special scenario. When phi and psi are both very small. In other words, small angular displacement. Okay? Now, small angular displacement is a common assumption in solving the pendulum problem, right? So for small phi and for small psi, since both of them are small, the difference between them is even smaller in general. So cosine of this angular relative displacement will be approximated by 1. Okay, so this is the new kinetic energy for small phi and for small psi. And again, we can rewrite this expression in terms of the matrices and vectors. All right. Okay. Now the potential energy, again, for small psi and small phi, we can approximate the cosine function by the first 2 terms. So we have this. Again, we try to rewrite the expression in terms of matrices and vectors, and we get this. And here we have a constant. Okay, so obviously the potential energy is already in diagonal form. Since this is only a constant, we can always reset the reference level for the potential energy so that this constant becomes zero, right? Potential energy can be reset by changing the reference level. Now, the kinetic energy is not in diagonal form. So we want to diagonalize the kinetic energy, all right? So we try to diagonalize this mass matrix. I call it mass matrix, okay? So solve the eigenvalue problems using the standard procedure that we discussed before. Then we have two eigenvalues, lambda plus and lambda minus. And then in terms of these two lambda eigenvalues, we can determine two normalized eigenvectors. All right, two normalized eigenvectors. Then we can obtain the transformation matrix, orthogonal transformation matrix, by making use of these eigenvectors. After transformation, the kinetic energy becomes in a quadratic form, diagonal quadratic form, okay? Because the mass matrix becomes diagonal now. The potential energy always in diagonal form, all right? Because it is diagonal already in the original expression. So kinetic energy, potential energy. Now you can see that combining these two parts, these two energies, we have the total energies. And the total energy can be split into two parts. The total energy of the particle associated to phi, and also the total energy of the particle associated with psi. The constant term can be thrown away by redefining the potential energy level, right? Reference level. So these two particles, transformed particle or transformed pendulum, become independent. And we know the solution for, we know the equation of motion for these two pendulums, right? And we know the solutions right away as well. It must be in terms of cosine and sine, because they perform, these two pendulums perform simple harmonic motion for small phi and small psi. All right, so we can write down the solutions right away and then impose the initial conditions to fix the arbitrary constants. All right, so far, all these three examples try to show that we need not to solve the Newton's equation of motion directly. By performing suitable mapping or transformation, we can always transform the original system into a form that is familiar to all of us. Say, simple harmonic oscillator motion, all right? Since we're familiar with the simple harmonic motion and we know the solution right away, so there's no need to spend effort. There's no need to make effort to solve the second order differential equations, okay? So say in the future when you are doing physics research, when you study physics postgraduate school, when you encounter physics research problems, the first thing to do, you will ask yourself, is it possible to propose a suitable transformation or a mapping or substitution in such a way that the unfamiliar research problem becomes a problem that is familiar to us. If that can be done, this is the best approach. You don't need to solve any complicated equations. What you need to do is to map the problem into one familiar problem, okay? So these three examples simply illustrate this point, All right. Now, let me see. I have some questions here. Must it be the case that after transforming the coordinate, the PE matrix, which is originally is still in diagonal form? Yes, yes, yes. So you don't want to ruin the potential energy's nice feature. So you have to pick a suitable transformation which will not change the diagonal form of the PE matrix. All right. That's why you can see that. You can see that when I choose, when I rewrite the the kinetic energy and potential energy, I choose this particular form, right, instead of this one. Okay. If you use this one, you may ruin the diagonal form of the potential energy. All right. So this is very important. This is very important. Is it to transform the time domain force to obtain an oscillating series in frequency domain? Samson, I'm not quite sure about this about this question. Can you explain it a little bit? Samson Leung. Samson Leung. Can you explain your question once again? Is it to transform the time domain force to obtain an oscillating series? I see. Yes, yes, yes. If the time dependent force is a periodic force, then it can be expressed in terms of a Fourier series, right? So that is exactly what you say. What if both KE and PE are not diagonal to begin with? Aha, this is more complicated. It will be more difficult to diagonalize both at the same time. In general, all right. But in some special cases, you still can do it if both KE and PE are not diagonal to begin with. So in general, it's tough, but we can still, in some cases, we can still do it. Oh, Jason Yuan, Jason, what do you mean by is it always possible to do it? Jason Xin Heng. No, it's not always possible to do it. Okay, if both are not diagonal, it's more tricky. Okay, you have to take care of both. Okay, it's not so obvious there, but in some cases you can do it. You can do it. We will encounter some of these examples as we go on, as we move on. So don't worry. Any more questions? Yeah, Jason, it's hard to make comments in general when KE and PE are not diagonal to start with. Oh, correct. All right. You have to look at the details of what problem. But my advice is, in most cases, or in those cases that you often encounter, either the kinetic energy is diagonal or potential energy is diagonal. All right. You encounter this kind of problems very often. If you encounter this kind of problems, then this systematic approach, this systematic approach of transforming the system is preferable. Now, if you have both non-diagonal kinetic energy and non-diagonal potential energy, then you have to propose a suitable transformation that will transform both to diagonal form, right? So, your question, I think your question is not like this. You are say in this problem, double pendulum, how can I know using this will destroy the diagonal form of the potential energy? Of course, you have to practice, okay? You try it and you find that it won't work, then you try to fix it, okay? And you realize that, if I put an extra square root here, it works, all right? So that's why, just like integration, if you practice a lot about the choosing suitable substitution of variables, then you're more skillful at finding a suitable substitution for a new integral, right? There's no systematic way. Why is the diagonal matrix not affected by the transformation? Because we have chosen the suitable column vector or suitable variable, so that the transformation will not be affected. I mean, the PG will not be affected by the transformation. You have to work it out by yourself, okay? You have to work it out by yourself, and you will see. It's hard to explain it here. Now, when you go home, you try this, okay? Try this expression, try this, and see whether it works or not. If it doesn't, and you ask yourself, why it doesn't work, okay? You in your calculation, you somehow see some minor deviations will occur, and that minor deviation can be fixed by putting this square root 2 here. All right. Now, in this particular case, is simple. In this particular case, all right. Now, if somehow this is diagonal, all right, this potential energy is diagonal. Okay, if you can fix it and make it look like an identity matrix, it works. Am I correct? No matter which transformation you propose. All right. So that's why I put in this square root 2 here. Now here I call it spring constant matrix. It's actually an identity matrix time 1/2 MGL. All right. But this is only lucky enough. We have this form. All right. It may not be always like this. You're correct. Wait, we need some guesswork to yeah, we still need some guesswork for choosing which mathematical tools are more appropriate. All right. In other words, we have to set up the stage suitable for the few mathematical tools that I have just shown you. So you have to do some background work, the foundation work, so that the mathematical tools that I have just discussed can be applied. Yeah, Jason, you are correct. I've just said that if the diagonal part, you somehow make it to identity matrix, it will be okay. But this may not be always the this may not be always be doable. All right, this is 2 by 2 is simple. If you are n by n, then you have to be careful. All right, but you can still do some changing, make some change of variables to fix the problem. But it needs practice. Okay. Any more questions? Yeah, here, let me reiterate. This won't work because this is diagonal only. This will always work because I have made redefined the spring constant matrix in terms of an identity matrix. Okay. But when you go to n by n, it may not be so simple anymore. Then we have to make use of another systematic approach. All right. Okay. We have overrun. So just let me know if you still have questions, or you can ask me questions next time on Thursday. Okay, any more questions? Number 1. Any more questions? Number 2. Any more questions? Number 3. All right. Okay, I see you on Thursday. All right. Okay, see you on Thursday. Bye-bye.